Welcome to part 2 of the lesson on properties of functions. Here we're going to start by talking about a property called continuity. It's often useful or helpful when you're describing functions to talk about where they have breaks or gaps or holes or something like that, and we refer to these things as discontinuities. So what does it mean for a function to be continuous? Well, a function is continuous on some interval if it does not contain any holes or breaks in that interval. Now, a discontinuity occurs when there's a break in the function's graph. And as usual, when we refer to where something happens on a function's graph, we do so by stating the x value at which it occurs. And that's exactly what happens when we state where we have a discontinuity. We talk about the x value at which that discontinuity happens. So let's take a look at some examples. Here's an example of a function that is continuous. Notice that it does not have any breaks or holes or gaps in it. And it also does continue, by the way, infinitely far on both the left and right sides. I didn't draw the arrows there, but it's implied that we have arrows at the end of that graph where it meets the edge of the grid. This is a continuous function. And we say it has no discontinuity, and it's continuous on the interval -infinity to infinity. What about a discontinuity? Well, this function here actually has some discontinuity, two cases of discontinuity, as a matter of fact. If you look at an x value of -2 and an x value of 4, notice that we have a break in the graph, right? It splits, those lines split the graph into pieces, and that's a result of vertical asymptotes. So we would say that this graph is discontinuous at x equals -2 and x equals 4. And it's perfectly acceptable to say this graph is, or this function is discontinuous at -2 and 4 without even mentioning x, because it's implied. You're talking about where something happens, so it's implied that you're talking about x values. What about this? Well, this is the equation for a parabola. And as we know, parabolas don't have gaps or breaks or holes in them. This function here is indeed continuous on its entire domain, which of course is all the real numbers. So there's no discontinuity, and it's continuous on the interval -infinity to infinity. What about the function y equals 1 over x? Well, you could draw a graph of this function, and hopefully you'll remember that it has a vertical asymptote that passes through the origin. So it passes through an x value of 0. And that means we have a discontinuity at 0, at x equals 0. And the reason for that is because we can't use an x value of 0. You know that if you try to substitute 0 for x here, you'd be doing 1 divided by 0, which we cannot do. That ends up, this graph ends up resulting in that vertical asymptote at 0. We can get very close to an x value of 0, but we can't actually use it. We just get really large positive or negative values depending on the sign of x. But the point is, this graph is discontinuous at x equals 0, and that's because it has a vertical asymptote there. And that's really it for continuity. Now, I should mention that the actual definition of a continuous function is slightly more complex than the definitions above. Now, in future lessons and in future courses, you're going to look at those other details, but for the purpose of this course, our definition here is sufficient, so we'll just go with that. Now, let's look at another property called symmetry. As you can probably imagine, it's good to know, and it might be useful to know when a graph of a function is symmetrical. And we have two different types of symmetry that we look at in particular, and I'll show you a couple graphs here to demonstrate those two types of symmetry. Take a look at the first one here on the left. Notice that we do have symmetry. Hopefully you see that we have symmetry about the y-axis. That is, the graph does the exact same thing on both the right and left sides of the y-axis. When this happens, we have something known as even symmetry. Now let's take a look closely at what that means. So here we have even symmetry. Okay, so what does that mean? Well, it means that if, for example, we are looking at an x value of 5 and an x value that is the same number but with the opposite sign, so -5, notice that these two x values give us the exact same y value. In particular, they both give us a y value of 5. And that will happen with any pair of numbers you use that are opposite signs. So for example, if you choose an x value of, let's say, 1 and an x value of -1, you get the same y value, which in this case looks like it's around -3. That is to say that if you choose f at -x, so like the negative version of x, and f at x, you get the exact same result. F at -x is the same as f at x. You get the same y value, whether you're choosing the x value or it's negative, its opposite is probably the better way to say that. That's even symmetry. Symmetry about the y-axis, same thing happening on the left and right sides. In other words, whether you choose an x value or its opposite, you get the same y value. The other graph here shows something called odd symmetry. This is said to be an odd function. Notice we do not have the same thing happening on each side of the y-axis here. For example, if you chose an x value of 4, that gives you a y value of -5. But if you choose an x value of -4, you get a y value of 5. Those results, -5 and 5, obviously are not equal. They are opposites. Now, will that happen for any x value and its opposite that we choose? Yes, it will actually. So for example, say you choose an x value of 1 and an x value of -1. So 1 and -1 are opposite x values. Notice that in both cases, we get a number involving 2, but an x value of 1 gives us a y value of -2, and an x value of -1 gives us a y value of +2. So unlike with even symmetry, when we have odd symmetry, f at negative something and f at that something without, its opposite, I should say, f at its opposite, are not equal. They are not equal, but they are opposites. So I can write in a negative here, and that happens. So in this case, when you have odd symmetry, what we mean is f at some value and f at the opposite of that value. So for example, x and -x, they give opposite y values, opposite results. That's why we have this negative here. And that's what odd symmetry is all about. Now, it's said to be rotational symmetry about the origin. That is, if I make this point, the origin here, a center of rotation, what happens is I should be able to rotate, say, this piece of the graph right around, and it will land on this piece of the graph. That's a property of functions that have odd symmetry. We get rotational symmetry about the origin. What's really important is you remember this. If we have even symmetry, f at -x and f at x are equal. So an x value and its opposite, when you substitute that into your function, you get the same value. With odd symmetry, you get opposite values when you use opposite x values. Okay, let's head back to our presentation and take a look at what we have there. What you're going to see on the screen now is pretty much everything that we just talked about with those graphs. Even symmetry, you have an even function if f at -x equals f at x. Now, what does that actually mean? It means if you evaluate the function at any number and its opposite, you get the same result. So f at -2, for example, will give the same result as f at 2. What does it look like? The graph of f at x is symmetrical about the y-axis. It does the same thing on the left side of the y-axis as it does on the right side of the y-axis. And here are some examples. You can see, for example, that this parabola does indeed do the same thing on both the left and right sides of the y-axis. Don't think that all parabolas are symmetrical, or don't think that all parabolas have even symmetry though. It only happens if your vertex is right on the y-axis. Okay, and the reason for that is because it has to do the same thing on the left and right sides of the y-axis. Okay, all parabolas are indeed symmetrical about some line, but it's not always the y-axis. All right, what about, the graph of y equals cos x or cosine x? Notice this graph does indeed do the same thing on both the left and right sides of the y-axis. For example, if I use an x value of 180 degrees, I get a y value of -1. Similarly, if I use an x value of -180 degrees, I also get a y value of -1. So same thing on both left and right sides of the y-axis. That is an even function. It has even symmetry. We can see it in table form too. Notice -2 for x gives us a y value of 16, and so does +2 for x, gives us the same y value. That also happens for -1 and 1 for x. We get the same y value of 8. Okay, so the same thing is happening on the left and right sides of the y-axis here. And of course, the y-axis is where we have an x value of 0. So this is an even function. Now, you might not know what the graph of f at x equals 3x to the power 4 minus x squared plus 7 looks like, but you do not need to know in order to determine if it is an even function. All we have to do is say, what happens if we sub in some value and also sub in the opposite of that value? Do we get the same result? Now, of course, you could do that for some number. You could substitute both, say, for example, 5 and -5 into this function and see what you get. However, one number isn't a lot of evidence. If we really want to show that this is an even function, we need to prove that you always get the same result for any x value and its opposite. And we can prove that by substituting in the opposite of x, which is -x. And when we do that, we just replace all of our x's with -x, just like if you were substituting in a number. If you were doing f at 7, you'd replace all the x's with a 7. Here we're substituting f at -x, so all the x's have been replaced with -x. But -x to the power of 4, well, that's a negative times a negative times a negative times a negative, which is a positive. We really don't need to write this negative sign. So let's simplify that. Same with this while we're at it. -x squared, well, -x times -x is going to be positive x squared, so we don't need this negative here. It simplifies to this. Now, take a look at our result here, which is f at -x. And our original function, which is f at x. Notice they are exactly the same. They're identical. And what that means is, if you sub in some x value, and you also sub in its opposite, you will always get the same result because we're working with the exact same function here. And when that happens, that is when f at -x is the same as f at x for every x value, we have the same thing happening on both sides, on each side of the y-axis. So we have even symmetry. So that's even symmetry. Quickly here, let's talk about odd symmetry. Well, we've already seen that a function is an odd function if f at -x and f at x are not equal, but opposites. They have the opposite sign for every value of x in the function's domain. And what does it mean for f at -x to equal negative f at x? It just means if you evaluate the function at any number and also the opposite of that number, you get opposite results. You get numbers that have opposite signs. So for example, f at -2 would give the opposite result of f at 2. What does it look like graphically? We saw this with our graphs. F at x has rotational symmetry about the origin. And here are some examples. This function has odd symmetry. You can see that because, for example, we get, let's take an x value of 1. You get a y value of 1. Now, if you use an x value of -1, you don't get a y value of 1, you get a y value of -1. Opposite results. We can do the same with 2 and -2. Those are opposites for x. What do you get? Well, a value of 2 for x gives us a y value of 1/2. And a value of -2 for x doesn't give us 1/2, it gives us -1/2. And as you can see, this is going to happen for any x value and its opposite. You're going to get opposite results. And that is odd symmetry. Here's the graph of y equals sine x. It's doing opposite things on the left and right side of the y-axis. So for example, an x value of 90 degrees gives us 1, but an x value of -90 doesn't give us 1, it gives us -1. Okay, so opposite things happening on the left and right side of the y-axis, that's odd symmetry. We can see it in a table here. Notice that opposite x values, for example, -2 and 2, give us opposite results, so 16 and -16. Same with -1 and 1. We get results that are opposite, 8 and -8. So that's an odd function. What if we have an equation? Well, we can do just exactly the same thing we did before. We'll substitute in a value of -x and see what that expression looks like. When we do that, we get this. Now negative x times negative x times negative x, so that's going to give us negative x cubed. And negative 7, or minus, subtracting 7 times negative x, we can rewrite that as simply as plus 7x. So when we simplify, we get this. Now take a look at that function. Is that the same as f at x? No, it's opposite. Notice that the opposite of 2x cubed is negative 2x cubed. The opposite of negative 7x or minus 7x is plus 7x. These are opposites, which means if you use an x value and its opposite, you will get results that are opposite. And that is what it means to be an odd function. So f at negative x does not equal f at x. It equals the opposite of f at x. All right, so we have an odd function there. And that is symmetry. Now, it's quite possible that you have a function that has no symmetry at all, in which case, if you substitute negative x into your function, you'll get a result that is neither the same as f at x, so it's not even, and it's also not the opposite of f at x, so it's not odd. And a really good example of that is one that looks like, well, let's do an example here. I'll just make one up on the spot here. Say we did f at x equals 5x cubed plus 7x minus 3. Okay, this function actually has no symmetry, and I can test that really quickly by substituting in negative x and see what I get. So I'll just do that right now. Oops. Okay, simplify that. Negative x cubed, well, I can rewrite that term as negative 5x cubed. Plus 7 times negative x, well, that's just minus 7x. Okay, notice this result is not the same as this result, but it's also not the opposite. If it was the opposite, this minus 3 would have become a plus 3 in this result, and it did not. So this function here has no symmetry. It's neither even nor odd when it comes to symmetry. One last thing to talk about, and that is the idea of something called end behavior. And all this is referring to is what a function's graph does at its ends. That is, as you go really far to the right or really far to the left. And when we do that, we have a special way of kind of talking about going really far to the left and really far to the right, and we use infinity. So if you're looking, at moving towards the right end of the graph, so for example, I was thinking of like walking on the x-axis in this direction, you are said to be approaching infinity. And we write it as x with an arrow infinity. It just means x approaches infinity. Whereas if you are walking toward the left end of your graph, you are approaching negative infinity. Okay, that's what the x values are doing. And that's how we state end behavior. We talk about what happens as you approach infinity for x, so you move towards the right end, and as you approach negative infinity, as you move towards the left end. So for this graph, let's take a look at what the ends are doing. What's happening as x approaches infinity? Well, just imagine yourself walking down the x-axis. What are the y values doing? Well, the further I go down this axis towards infinity, notice the y values get higher and higher and higher. So the y values are approaching infinity. So we can write that. As x approaches negative infinity, what's happening to our graph's y values? Well, as I approach negative infinity, I'm walking on the x-axis towards negative infinity. What's happening to the y values at the end? Well, eventually they get lower and lower and lower. And the further I go towards negative infinity, the lower the y values end up getting. So we say those y values are approaching negative infinity. I don't want you to think it always involves approaching infinity, though. Take a look at this exponential function. Here, as x approaches infinity, so taking a walk this way, what happens to the y values of the function as I go this way? Well, they get really, really low. So yes, I am approaching negative infinity. But what happens as x approaches negative infinity? That is, as I walk this way on the graph. Well, it looks like the y values are getting closer and closer and closer to some number. And we know that's true if this is an exponential function. There's an asymptote, looks like at 3 here. So those y values are getting closer and closer and closer to 3. So as x approaches negative infinity, the y values are approaching 3. Last but not least, let's do one example involving the absolute value function. Now the absolute value base function, that is y equals absolute value of x, has both of its ends pointing upward. This transformation will make those ends point downward. It's a vertical reflection. All of these other transformations, a vertical stretch, a horizontal shift 6 units to the to the left, and a vertical shift 8 units up, all of those transformations will have no impact on the fact that the ends of this function point downward as they go out to infinity and negative infinity on the x-axis. So we can say for this particular function, as x goes to infinity, we know that that right side of that graph is pointing downwards, so the y values are approaching negative infinity. And the same thing's happening on the left side. As x goes to negative infinity, the graph is pointing downwards, and it's achieving lower and lower and lower y values that are negative. So it's approaching negative infinity for y. And that's the end behavior of that absolute value function there. And if it helps, just draw a little graph. It doesn't have to be a really good, accurate graph, but just start with your base function and start applying some transformations to do a rough sketch to see that, yes, no matter if I'm approaching infinity or negative infinity for x, my y values are approaching negative infinity. And that is it. There is our lesson completed on properties of functions. Now, the most important thing to do at this point is to get a lot of practice using this language. So be sure to do a lot of practice, look at a lot of examples, and if you're stuck, be sure to ask lots of questions. There you go. Take care.